Once we know the level of stress in the structure, we can apply a suitable failure criterion. That's the topic of Module 25.
So we have just seen that there are several analytical models that can determine the stress in the adhesive. Now we can apply a suitable failure criterion. But first of all, let's understand the failure modes, and then we can see the failure criteria. And the joint can fail basically in three ways. It can fail in the adhesive, we call cohesive failure in the adhesive. We can live with that. It can fail due to a lack of adhesion, we call adhesive failure or interfacial failure. We cannot live with that. We cannot design a joint that fails at the interface, and we have seen that in the theory of adhesion, that the work of adhesion, when the surface treatment is properly done, is higher than the work of cohesion. So if this happens, this is a problem of production, basically. It should not happen. And finally, you might have a cohesive failure in the adherent. This is the ideal situation, and I can also live with this. So let's start with the cases where the failure is dictated by the adhesive, where the failure takes place in the adhesive, all right? And we have basically three situations. When the adhesive is very brittle, when practically the shear strain curve is elastic up to failure, then you can use a stress limit, and you can use the Volkers or Golein-Reissner models. When the adhesive has ductility, some ductility, something like this, then you can use Hart-Smith, and it fails when the strain in the adhesive reaches the failure strain of the adhesive. And then you have the cases of the very ductile adhesives, typically more than 20% in shear. In this case, you don't have to worry about a fancy analytical model. The adhesive will fail simply because you reach global yielding. That means the adhesive has yielded all the way through the overlap. And in that case, it's a very, very simple equation to use. And that's precisely what is shown in this slide. So on the left, you have the situation previously described in the case of Hart-Smith model, which says when you reach the failure strain in adhesive, it fails, which is indicated here. This has all gone plastic, 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 plastic. So this is plastic in the joint. This has yielded in terms of stress, and all this part in terms of strain has yielded. And it fails because here, in this point, you reach the failure strain of the adhesive, okay? Failure. Okay, but now imagine that the adhesive is much more ductile, then it can still take more, and the plasticity will go inside the joint until you have global yielding. The whole joint has deformed plastically. In terms of strain, the whole part has plastically yielded. In that case, when you reach global yielding, of course, the adhesive cannot give anymore. It's completely yielded, and the failure load is simply given by the yielding stress of the adhesive times the resistant area, the overlap times the width. And you would be surprised to see how much this is precise. And this works for very, very ductile adhesives. In terms of the load displacement curve that you register in a single lap joint that is being loaded, if it's elastic and has practically no plasticity, then it fails somewhere here. If the adhesive is ductile, the more ductile it is, the more load you will get. So really, you like ductile adhesives, and the more ductile, the better, because you make use of the whole overlap, and you have proportionality between the overlap and the failure load. Okay, let's see now what happens when the failure initiates in the adherent. And we have two cases to distinguish. The case of low-strength metals, where the failure is controlled by the yielding of the substrate, and the case of composites, where you have delamination, or you might have delamination of the composite. But let's start with the yielding of the metals. Again, where is the location in the metal where the stress is maximum? It's the ends of the overlap. All right, we know that. And if you are talking to a low strength metal like mild steel or like aluminum, low grade aluminum, then you might have or you might reach yielding of the metal here at the ends of the overlap, and you have the creation of a plastic hinge, and then the plasticity will be concentrated at that point, and it will pull locally the adhesive until it fails. But really, what initiates failure, what controls failure, what limits failure is the yielding point of the metal. And if you want to have a good prediction in this case, you simply have to determine the load corresponding to initial yielding of the metal. I'm going to show you two cases here. You have the case first where you have absolutely no yielding of the steel and the whole adhesive has yielded. We are talking about a two-part polyurethane, very, very ductile, and you can see it's rough, the failure surface of the polyurethane, because it has all yielded. So you did a test, it failed, and it's very clear that the whole overlap has contributed. Fantastic. That's exactly what we want. Now, imagine you take a mild steel. Mild steel, it will deform plastically during the test until it fails. It will fail in the adhesive, but what initiated failure really is the plasticity of the steel. Can you see how bent, deformably bent, and permanently? Okay, this is the situation described in the slide, in the current slide. Plastic deformation of the adherence. Now, how do you calculate the load corresponding to initial yielding? This is basic mechanics of solids. You have two components. You have the longitudinal load. You are loading the single lap joint like this. The substrate will be loaded in this direction, so it's simply the load divided by the resistant area, the width times the thickness, easy peasy. But you also have the bending stress, so you have to sum the two components, the longitudinal stress and the bending stress. About the bending stress, you can use the bending moment factor K, defined in Gola and Reisner. If you remember, in the previous module I talked about that. And this K, we will see, there is a complex formula, but we can simplify. But anyway, if you sum this plus this, and you give the load as at the moment when the stress in the substrate reaches the yielding point, this is the final equation, okay? Load, the maximum load, will be the load corresponding to the moment when the stress in the adherent reaches the yielding stress of the adherent. Okay, so let's represent this in a graph where we have the failure load versus the overlap. For K, we can simplify and we can say that for low loads and short overlaps, K equal 1, and we are at this point here. For joints which are long compared to adherent thickness, typically a relation of overlap divided by the thickness equal 20, we can assume that K tends to 0. And then we are at this point here. And this is this equation simplified when K equals 0. So from this point, we have this horizontal line. In between the two, we can join the 2 points. And then we have the limit corresponding to the yielding of the substrate. On the other end, or on the other end of the scale, we have this line corresponding to perfect proportionality between load and overlap, which corresponds to the global yielding of the adhesive. So if you have a very ductile adhesive, the substrate is very strong, like high strength steel, the steel will let the adhesive work in peace, and you have this limit. Now, if you take the same adhesive, very ductile, but a soft material like mild steel, the adhesive will not work in peace. It will be limited by the yielding of the steel. Again, you would be surprised to see how this is precise for the case where you have yielding of the metal. But this is the subject of the next module. let's see now the case where you use composites. Composites, fantastic materials, magic materials in the direction of the fiber. You have strength comparable or even more to the case where you have high strength steel. Great. But the problem is the through the thickness strengths. The through thickness strengths basically is controlled by the resin. An epoxy, for example. And the epoxy is not that strong, 50 or maybe more, 60, 70, say 80. But still it's a low value. And when you load the joint, you know that you have peel stresses in the adhesive as well as in the composite. And these peel stresses might be enough to cause delamination of the composite. And in that case, it's not the adhesive that controls failure, it's the delamination of the composite. And if you want to have a good estimate of the failure load, you simply have to calculate the load corresponding to the moment where you have delamination of the composite. And again, you would be surprised about the precision of the failure load that you obtain that is very comparable to the experimental failure load. Again, I have a situation, an example here where you have delamination of the composite, you see? Everything happened here and here at the ends of the overlap by delamination of the composite. This typically happens when you use a stiff adhesive, like an epoxy. That's why when you use composite, it's better to use a less stiff adhesive to avoid too much stress at the ends of the overlap so that the adhesive can work and can give its full potential. All right? So, we have given the main analytical models. We have talked about the major failure criteria, whether in the adhesive or whether in the substrate, when it's the substrate that controls failure. But it's a lot of equations, a lot of approaches. That's why we decided to make a software, a joint design software, which combines everything and will tell you for a particular geometry, for a particular type of adhesive, very ductile or brittle, for a particular type of substrate, metal or composite, which failure criterion is the most adequate. There is nothing new in the software. The new thing is it's very user-friendly and it will tell you what is the model to use for a given situation.
Here we are going to start with a demonstration of our Jointdesigner software. This is an online software that allows us to predict the strength of multi-joints using analytical models. Let's start with a new analysis. We're going to consider the single abstract geometry, and we are then faced with a menu that asks us about the material behavior. We're going to say that our joint has adherence with an elastic behavior and an adhesive with also an elastic behavior to keep things simple. Then we also define an isotropic behavior, so there is no directionality of the properties of the materials. Then we are asked for a load intensity. We're going to start with 1000 newtons, and this will create the stress distribution that will result from this target load. Module number 3 is the material properties model. Here we are going to select materials. So for the adherence, we are going to consider steel, which is already pre-selected here in this list. And then for the adhesive, we're going to consider, for example, RLD 2015, a common epoxy adhesive. Module number 4 will take us to the selection of the geometry of the joint. And so we're going to consider a joint with 2 millimeters of thickness in the substrates, with an adhesive layer thickness of 0.2 millimeters, and an overlap length of 25 millimeters by a width of 25 millimeters. In module number 5, we see a selection of possible analytical methods to solve this problem. This selection is a function of these characteristics here in module 1, because these models that you see here are also models that account for these characteristics that we see here, elastic behavior and isotropic behavior. I'm going to select one of the most classical ones, which is the Volkersen model. Then, according to the selection of this model, we are asked for a failure criterion. This failure criterion will be the maximum shear stress. And if we know that our adhesive has a maximum shear strength of 14 MPa, we can introduce here this given load. We click compute, and we get a stress distribution along the overlap length, and we get a limit line which corresponds to this failure criterion of 40 MPa of stress in shear. The only thing that we need to do is go here to the right side and now change gradually the load that we are applying to the joint. So for example, 3000 will generate 8.32 megapascal, 4000 a bit more, and let's go all the way up to 6000, and now we have passed our limit. So we know that it should be something around 5000, probably 5050, something like this. Okay, and so with this we have calculated, using the Volkerson method, the load that this joint will support before the stress in the adhesive layer reaches the maximum that the adhesive can sustain.